All right, last lecture. So as I tried to describe to you guys last time, there's going to be 7 topics on test 3, and we hit 4 of them last time, so we got 3 to go. And our 5th out of 7 is going to be potential flow with some cylindrical coordinates, and that's in chapter 6. There's a lot of material there. We're going to narrow it down to one basic case and ask you guys to be able to do a few calculations and a little conceptual work with that. So before we get going, let's just go ahead and take about 5 minutes to do an example to review this idea. So basically what we want to be able to do is just take a look at some fluid flow. So imagine you're above and looking down at a river or something like that, and be able to describe it conceptually and then get some mathematics behind it. And that turns out to be helpful for a variety of reasons. So without stressing about it, I'd like you to just think about a case where we had a flow that was described as follows. There's the velocity vector, 2I, and it holds between 0 equals y from 0 to 4. And ideally, we'd like to be able to do the following. Graph some velocity vectors. Think about what the streamline looks like. Could we come up with a streamline function? Ask ourselves, is it potential flow? Okay. Think about what the velocity potential function might look like and graph some potential lines. So you might say, wait a minute, whoa, this is going to be the hard topic out of the 7. Actually, we're going to make it really easy. So I'd like you to pause for a second and just think, okay, first thing, could I do the following? For this for this velocity vector, could I graph a few velocity vectors? And I'm going to pause and get that up there. So this expression right here, v equals 2I, in words it's saying the velocity everywhere is 2, say meters per second, in the x direction. So I've drawn some velocity vectors in the x direction. The problem says it only holds from 0 to 4, and everywhere the velocity is in the x direction. There's no velocity in the y direction, and everywhere the velocity is the same length. So what is this case? This is a case of uniform flow. It might be a flow between 2 plates, and it's in viscid flow because ordinarily we would have slower flow there and there. All right, not so very bad. Okay, what do the streamlines look like? Well, why don't you go ahead and do a new drawing where you draw a few streamlines. Streamlines are supposed to represent the path that the particles are taking. So particles of fluid are moving to the right. So we would have streamlines going like that. If we tried to move from graphing the streamlines to get a streamline function, well, this could be something like y is equal to 1. This one here could be something like y equals 2. This here could be something like y equals 3. And remember that stream function basically gives us a streamline expression that we can set equal to various constants. So it might be possible in this case that our streamline function is something like this. Okay, not going to worry about that for now. Main idea is to get to what's going on with the streamline shape. Okay, this was a little bit challenging to get our minds around, but is this potential flow? Turns out it's irrotational and we could get that. So what does the velocity potential look like? And I'm going to get an equation up there in a second that will be important for what we're going to do. See if you can remind yourself what the relationship in between the velocity potential and the velocity vector is. So this would be good to remember for test 3, okay? When we model flow, there's something called the potential function. And if we do the gradient of the potential function, we get the velocity vector. For Cartesian coordinates, and this is not for test 3, but for a quick reminder now, the way you get the gradient of the potential function is you do the partial of the potential function with respect to x times I hat, partial of the potential function with respect to y, j hat, and of course if we had 3-dimensional flow, there'd be a z. Well, I would like you to give it a try then, and given that this is the velocity vector, see if you can go backwards and get the potential function, and I'll be working on that out myself. Okay, well, here's the math. d phi dx is the component of the velocity in the x direction, okay? And in this particular case, the component of the velocity in the x direction is 2. It's always going 2. So I can say v at x is equal to d phi dx is equal to 2. And going backwards from that, I know that just going backwards and doing my integration, that the potential function would be equal to 2x. Now, I didn't take care of the y component, but if you take a look at how much velocity is in the y direction, there's 0. We could add a c on there, but the general convention there is that we just ignore the plus c, and there's going to be some function phi at x, some potential function phi, which is 2x in this case. And we can get the equipotential lines, our last step, by setting phi equal to various constants. So let me just give an example really quickly and see if we can get it up there. 2x is equal, let's pick the easiest number possible, 2. So what would that look like? That would be equivalent to the equation x equals 1. And what does x equal 1 look like? Well, that is a vertical line through x equals 1. So we would add a vertical equipotential line here like this, another equipotential line maybe at 2x equals 4, etc. We'd have equipotential lines looking like that. And hopefully you remember the idea that the equipotential lines are perpendicular to the stream. Okay, so I'm sure that all seems very, very abstract, and it is a little abstract, but if you look through chapter 6, there are some pretty challenging flows that are very practical, then can get modeled by combining different types of basic flows. Like I'd like you to imagine a vortex where some flow is swirling and spiraling in and going down. Well, that could be a combination of spiraling motion, which there's a way to model, and linear motion down. And if you could, the easiest way, mathematical way to do it is to take two potential functions and then combine them. And we're not going to get to that. That's the section in the book called superposition. But in general, we want to be able to take potential functions that are Cartesian coordinates. We did that earlier. And also potential functions in cylindrical coordinates. That's all I wanted to introduce to you right now in the next 20 minutes. And that's all we're going to have you guys do on test 3. So let's get started on that. All right, so for starters, a quick reminder. See if you can go ahead and do this on your own. How do Cartesian coordinates work? Well, ideally, if we were really detailed, we could do 3 dimensions. We're going to do 2 in this class. But why don't you go ahead and graph the point 2, pi over 6, 3. And I'll give it to you a little bit by little, but see if you can pause the video and remember how to do that. Okay, let's just go ahead and be a little rough with it. Reminder, oftentimes in cylindrical coordinates, the first value given is r, how far we go out in the r direction from our origin. The second direct number is a rotation, an angle, and the third is how far we are in the z-axis. Okay, so one way we could think about it is if we oriented our axis to the right and our z-axis up, 2 would mean from this origin we go out 2 units. Okay, z would mean we go up 3 units, but I'm going to go ahead and do the rotation first. Pi over 6, hopefully you remember that's 30 degrees. That's in the positive direction, so I could put my thumb in the positive direction and rotate, curl my fingers indicating, so I'm rotating this way 30 degrees. Okay, so let's say that's 30 degrees, and then from there I would end up going 2, and that would be my point right there like that. My point over 2, rotate 30 degrees, up 3. All right. Breathe a sigh of relief. ME120, just 2 dimensions. Which one of these 3 are we going to eliminate? We're going to eliminate the z dimension. So we're just going to imagine that we have flow in the plane, okay? And so you can just imagine there being an r axis here like this, okay? There's my origin, okay? And then theta would be rotation from that r axis. So if I was going to do 2 pi over 6, I would go out 2. And then I would rotate 30 degrees like that at a constant radius of 2, and there would be my point like that. All right, what we want to do is velocity vectors. We're just going to stick with 2 dimensions, so I would encourage you to write this down. Okay, we're going to work with velocity vectors at any point in the plane, at some point r theta, and the velocity vector is going to have a velocity in the radial direction, plus a velocity in the tangential or theta direction, e theta. All right, it's been a while since vector calculus. Let's do an example that looks like a very easy equation. What we're going to do is even be simpler. So if we get this, we're on our way. Okay, so why don't you go ahead and graph this? Why don't you go ahead and write down this velocity vector? When would fluid ever do that? Don't worry about that for now. and I want you to graph it at 2 points. I want you to graph it at 2, 0, where this is a point r equals 2, theta equals 0. And then we're going to do it at 2 pi over 2, and we're going to put both vectors on the same graph. So I'm going to do it little bit by little bit. I encourage you to pause the video and see if you get the whole thing yourself, but if you get stuck, take a partial look. All right, the reminder here might be useful. I've defined an origin. I've defined an r direction. These dotted dashed lines essentially would represent different angles, okay? Not very well drawn there. Let me just redraw that like that. So this might be pi over 4. This might be pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, etc. So those are different angles we can rotate. So at this point, 2, 0, I go out 2, I rotate 0. So I'm right there like that. I want to try to draw this velocity vector, and it's got a component in the radial direction, and it's got a component in the tangential direction. Give it a shot. Okay, let's give it a try really quickly. Okay, the component in the radial direction is the radial value there, and this is r equals 2, so we would have a component in the radial direction like that. Okay, what about the component in the tangential direction? This one says it's always equal to 2. It's always equal to 2, so there would be a component in the tangential direction, and the tangential direction or the angular direction would be like that. Okay, this is the theta direction like that. So there would be our other component, and we would get a resultant. I haven't drawn it very well, but it would be it would be a 45-degree line out like that. And that would be the resultant velocity vector at that point there like that. Hey, that's probably good enough. You can probably if you think about B, it would be at the point out 2, rotating pi over 2, and you could probably get it from there. Just really quickly, what is the r value? 2, so there would be 2 out in that direction, there would be 2 out in that direction, and we would get a rate vector like that. Don't stress, that's a quick reminder. So the next thing is an equation to write down, just a little bit of meaning behind it. What I'd like you to be able to do is take a look at one main type of potential flow for cylindrical coordinates and go from the potential function to the velocity function and do a little bit of graphing. So a reminder, basically, if you want to get the velocity vector from the potential function, we're going to do the gradient of the potential function, but that has a different form in cylindrical coordinates. So basically, here is our governing equation, and then what we need to do to get the velocity vector, we need to get VR and we need to get V theta. So VR is probably what you might guess it is. Okay, I'll give you a potential function. How are you going to get VR? You're going to do the partial of the potential function with respect to R. Okay, how are we going to get the velocity component in the angular direction or in the theta direction? V theta. Okay, it would be so nice if it were just the partial of the potential function with respect to theta. Okay, but in addition, there is a 1 over r in there. Okay, there's also a component in the z direction. Okay, we're not going to worry about it in ME120. This is equation 6.70. Should go on your equation sheet for test 3. Let's work with it. Okay, so if you're trying to build a bag of tricks for modeling flows, probably one of the first things you would start would be uniform flow, like a stream just going down in a certain direction. Then you might incorporate a little bit about viscosity, etc. But we're chapter 6, we're in viscid flow, where we don't have viscous effects. Probably one of the next most common components of some sort of complicated flow is what's called a source or a sink. So let me talk about that really, really briefly. Let's imagine there's a sink and we've got plane flow. So there's some water or some sort of fluid in this plane, okay? Those dots represent, bits of water. And there's a hole right there that is slightly lower and they can go down. Well, what are they all going to do? They're going to actually flow towards that hole and end up going down the sink. So you're going to get a continual flow going in and going down into that sink. Okay, well, a source would be the opposite, where maybe we have something that actually creates some fluid coming out of this hole into this plane, and every bit that comes out would actually flow out radially if that plane were horizontal. And so that would be, this would represent source flow, and this would represent sink flow. And that is kind of our first step in chapter 6 in modeling. They have several potential flows. I hope that for homework number 10, you just take a little bit of time in looking at it. But the one we're responsible in this class for is 6.82. And the potential function for source or sink flow, okay, is, well, you'll take a look at it. You've got m over 2 pi. And this will seem surprising at first. It's got a natural log of r. Natural log of r. Go ahead and write that down. M represents some sort of constant. And a crucial thing we'll ask you to practice a little bit for homework and then think about on test 3. What difference does it make if m is positive or if m is negative? Okay. And what I'd like you to do, the next thing's not in the textbook, but I'd like you to put in parentheses is equal to essentially some constant times ln r. Okay, and that is the type of equation we're going to ask you to work with. All right, and that is the last equation that we have for this topic. And here's what we're going to do. We're going to take an example and work our way through it. I'll get it down there and describe it, and then we'll get you guys working. So the first part of it is I'm going to give you a potential function, okay, at r and theta. Okay, and I'm just going to make it pretty simple to start with. I'm going to make it 12 ln r. Well, actually, not to start with. That's the entire problem. Okay, I'll get you set up on it in just a second. I would like you to pause and see, look, can you figure out the velocity vector for that function? Can you figure out the velocity vector for that function? It involves just the two of the basic equations that we got up earlier. Okay, hopefully you've made some progress, but let me just detail what we're going to try to do completely in this problem. We're going to try to come up with a velocity vector equation. We're going to try to fill out this chart. At r equals 1, 2, 3, and 4, what is the radial component of the velocity? What is the angular component of the velocity? We're going to fill in numbers there, okay? We're going to say, hey, is this equation modeling a source or a sink? We're going to try to graph the equipotential lines. And finally, we're going to try to think about what the streamlines look like and what would a streamline equation be. All right, give you a second. See if you can make some progress on that. All right, so bottom line, you've got, excuse me for a second, these two equations to think about, and we're going to apply them to this stream function right here. So the first thing we're going to do is do the derivative of this function with respect to r, and derivative of ln r is 1 over r. So we're going to have 12 over r, okay, and that is the component of the velocity in the radial direction. So that would be e hat r, okay. All right, and then to get the component in the angular direction, or maybe the tangential velocity you could call it, we don't want to do 1 over r times the partial of the stream function with respect to theta. That doesn't have a theta in it, so that's 0. So we are done. If you got that, 100% on the first part. Okay, really quickly, why don't you go ahead and fill in that chart, and I'll get it up there in just a second. Okay, there's at our first radius, okay, at radius of 1, the velocity in the x direction, pardon me, goodness, in the radial direction is just going to be 12, and there's no tangential velocity, so it'll be 0. And you can fill in the rest of these. This is going to be 6, this is going to be 4, this is going to be 3, and they're always going to be 0, 0, 0. Okay, is this a source or sink? Well, that comes from a little bit of visualization. So I'm going to draw myself an r-axis and maybe put in a couple dotted lines and imagine that I'm looking overhead here like this. Okay, so let's do r equals 1. Okay, what does it say that the velocity is like? It's 12, and it's positive 12, so it would be in the positive direction. So it would be out there like that. Okay, how about this point right here? This is also r equals 1. It would be out there like that. And over here, this point is also r equals 1. They're all r equals 1, and the velocity is all outward. Okay? And we could do another graph for r equals 2, basically it would show the velocities all going outward, but not as fast. And the same thing with 3 and the same thing with 4. So this is a source. This is something that's creating outward flow. Okay, why don't we pause for a second and see if we, just to this little graph that I have going here, if we could add an equipotential line. And just a reminder, that's where we take this stream, this velocity potential and try to set it equal to some sort of convenient constant and see what the equation gives us. Okay, well, 0 is an awfully convenient number, so I could put 0 over there and try to work it out. But I'm going to do something a little bit different. I'm going to do 12 and see if I can take it from there. So I'm going to try to solve that for R and visualize what the graph looks like. So thinking about it a little bit, then that we would get ln R is equal to 1. That's equivalent to log base E of R is equal to 1. Okay, and if you go ahead and solve that, that means that R is equal to E. And what is that? R is equal to E. That's a number. That's just basically saying R is equal to 7 or 3, or in this case, 2.718. So what does a graph look like in polar coordinates where R is equal to number? And yeah, it's just a circle. It's just a circle. So I would go out to some point here like this and just try to carefully draw in a circle. And that would be an equipotential line. And hopefully you remember that the equipotential lines are always perpendicular to the direction of velocity, so it seems to fit. Okay, finally, what would the streamlines look like? Okay, if we were, I'm going to go ahead and eliminate these red vectors. Okay. Well, hopefully you have the idea that basically what we have is a source here with fluid just going out. So we would have a streamline going out like this, a streamline going out like that, a streamline going out like that, a streamline going out like that. And everywhere it would be perpendicular to the equipotential lines. And those would be our streamlines. Okay, so hey, in polar coordinates, what does that equation look like where we have a line that goes out like this, okay? And is there something constant about that line that I just outlined? And in fact, it's actually that its angle is constant. Its angle is a constant. So the streamline equation would be of the form, remember a streamline equation, our symbol is that, and it would be the form theta, where theta could be various constants. Okay, hey, we're done. What are you responsible for? You're responsible for understanding the form of the velocity vector in polar coordinates and how to go from a potential function to that velocity function and do a little bit of graphing. We'll give you some homework practice with that on homework 10, both looking at some nice pictures in the textbook and just a little bit of graphing and computation. We are counting down, so 7 topics. And number 6 out of 7, lift, section 9.4. So really similar to drag that I went over before test 2, and I got to say that there was a lot of really great work on test 2. I can tell that a lot of you guys worked hard, went through the material, did some good practice. And the drag stuff went pretty well for a lot of you, and I think the lift stuff is going to go as well also. It's going to come down to one basic equation, but once again, you need to be careful about the particulars. So, but before we get going, I also would love to ask a conceptual question about it. So, same idea. We're going to use U we're going to think about our object. This could be a section of a wing that is going to somehow be lifted up by its interaction with the fluid. We're going to think about, we can visualize any particular situation, thinking of the object as being stationary and the fluid is moving relative to it. So the conceptual thing is to start by taking some point, like let's think about that point there, and I've blown it up right there, and draw the shear vectors and, the shear vector at that point and the pressure vector. I think it's easier to start with the pressure vector and then get the shear vector. So go ahead and do that, 2 vectors on the same point, thinking about lift and drag. All right, well, there's the pressure vector. Pressure is always perpendicular or normal into a surface. And what we want to do is break it up into components. Drag would be essentially opposite the direction our object wants to go. So this is a wing, we would want it to be flying that way, and it would be opposite. So this would be drag here like this. And then this other component of the pressure, the up component, this would be the lift here. Obviously, we want this shaped so that we get mostly lift from pressure. Okay, what about shear? Okay, well, there's that no slip condition, and the fluid right here is not moving. This fluid next to it is moving relative to it, and this might be what the shear vector would look like. hey, this is a blown up version of that shear vector. Do we get any drag? Do we get any lift? Well, there'll be a component like this, and that's drag, and there'll be a component like that that's opposite, and that is inhibiting lift. It's not as bad as we think, though, because remember, if we're doing something like air is not very viscous, and as a consequence, the shear forces are not very large, and so the pressure forces are going to dominate, the lift is going to dominate. Even for water seems pretty viscous to us, but amazingly, if you get into kinematic viscosity, you're going to notice that it's going to be okay, and we're going to get the lift that we want from the pressure force. Okay, that's theory, and some of you might be saying, wow, that chapter 6 stuff seems pretty abstract. But if we want to get everything modeled correctly, it takes a little bit of work. We're going to do some gross overall stuff and get away from having to go point by point. All right, but before we do that, I would like to take a look at 2 other points then. I would like you to take the very, very top point of that section of a wing. So that's a section of the wing, and by the way, it's supposed to be a complete wing. And then also, why don't we do the corresponding down below, point down below? Okay. And all I want you to do is get the pressure forces and decide whether we're going to get any lift. So there's the arrows, not bad. Probably the bottom one, if we were somewhere near sea level, would be 14.7 psi. And if it's atmosphere, and this one here, man, if it's 14.7 psi, we get no lift. But it turns out that one way this is thought of is by taking the Bernoulli equation, thinking about the Bernoulli equations. These vectors here are probably pretty much uniformly going to head, this wind is going to pretty much uniformly go like that. But here we've got some squeezing going on in this area, and these vectors need to fit through there. So there's this idea that they actually need to speed up as we get through there. And remember, from the Bernoulli equation, we tried to capture that idea that some fluid could have some pressure energy, some dynamic pressure, or some speed energy, and it can have some elevation energy. And if we end up gaining speed energy, we end up losing pressure energy. So if this airfoil is properly shaped so that the air moves faster on the top than on the bottom, we get a decrease in pressure on the top, and that differential over a plane wing is enough to lift up a plane. Pretty ingenious discovery, and it's interesting to look in the details in chapter 9. All right, besides this conceptual stuff, I said it came down to one equation, and you guys can probably finish off that equation. It's very similar to the drag. So how are we going to get a lift on an object? Well, fluid engineers, fluid dynamicists love to use this 1/2 rho u squared. It's the dynamic pressure. It basically characterizes the energy of this flowing unit in units like PSI or newtons per meter squared. Okay, so let's say if that's PSI and we want to get a lift in pounds, we need to multiply it by an area. Okay, well, maybe not all this pressure is converted into force. That's one way of thinking about it, so we have a coefficient, all right? And I'm missing one term in my coefficient, and this, before we had the coefficient of drag, which was a sub d, this will be a coefficient of lift, and there is our one equation for that we're going to use for our computations on lift. Deceptively easy. So, key things. Rho, what is rho? That is the density of the fluid that the object is in. What is u? It's the relative motion of that air or fluid to our object. Okay. What is a? Okay. Well, it varies in various applications, and for things like wings, and that's what we're going to focus on for test 3. The area is called the planform area. So let me write that down. Planform area. And so you might want to make a note of this, wings, okay, 4 wings. Okay, and basically what it's going to do, we're going to take how long the wing is in a section, in a sense, which would be the length from the front to the rear. And the symbol that your book uses for it is C. And then we're going to also take a look at how long it is in this dimension, which the book uses B, the letter B for that, okay? And so our planform area is going to be A is equal to B over times C. And the way I've usually seen it described is that, like, suppose you're up above the plane and looking down at the wing. What is the area that you see looking at that? And for, obviously for planes, that's going to be a really, really large area in some cases because we're trying to lift a plane off the ground. Well, we're going to ask you to use also for wings to think about drag. And so the drag equation, let me get that back up there. Okay. There's our drag equation, same thing, okay, same terms. But what is the A going to stand there? Well, conveniently, the way this has been done historically with plane wings is the A there is the same area. So if you're doing a problem where you need to figure out both the lift and the drag for a wing, once you figure out that B times C, that area, or if it's given to you, then you can use that area for both the drag and the lift. Okay, before we get some practice, let's go ahead and take a look at what do these C's look like? What are the numbers like? And for that, I'm going to ask you to take a look at some tables in chapter 9. Well, for starters, what should CD be and CL be like for a good plane? Well, D is drag, so we would like this number to be really low. And L is lift, we would like that number to be as high as possible so we don't have to make our planes very big, wings very big. And there's a lot of great graphs in chapter 9 that talk about CL and CD for various geometric configurations, et cetera. As you can imagine, it's quite complicated. At the most, I'm going to ask you to do is read some graphs. One graph is 9.35a, which on the x-axis has the angle of attack, which would be the angle between the horizontal and the angle, essentially the line going through our wing there. So there's that alpha in that case like that. And alpha can be positive or negative. And it's kind of interesting if you look at it, alpha goes up to 8 degrees. You don't want a wing much above 8 degrees according to this data. And you can get points at positive CLs, at positive angles of attack, where CL over D is huge. It's in the order of 60 times greater. At 0, if an airfoil is properly measured, we still get a positive CL over CD because we get that effect where the air is going faster on the top and the bottom. And it can be possible to get a negative CL over CD. And so what that would mean is that at some sort of angle where the plane wing, excuse my drawing, is down there like that, well, instead of getting lift, we're getting down force actually, and the plane wing's actually getting pushed down. All right, let's work an example. All right, next to last example of the year, let's do a plane wing problem. So we got a plane going through 59-degree F still air at 440 feet per second, 300 miles per hour. So that's less than the speed of sound. And how are the numbers going to work out? So the plane wing dimensions are given by C equals 8 and B equals 60. The coefficient of drag is a typical number. And from some sort of chart, we get that the ratio of the lift to the drag is 50. Let's get the drag and get the lift. Look, you can do this any way you want. One way to approach it is start by getting the dynamic pressure, and I'm going to do that quickly. Okay, so 230.4 is what cranks out on my calculator. Hopefully you've seen this enough that if this is in slugs per foot cube and this is in feet per second, that ends up being a pressure in pound per foot squared. In this case, we don't need to convert it to PSI. Hey, let's get the drag. Okay, so the drag is going to be our coefficient of drag times this term that we already figured out times our area, and this is the plane form area. So we're just going to go ahead and crank through that. I'm going to take that number, and our coefficient of drag is low. Ordinarily, we would be worried about this stagnation, this energy, or this dynamic pressure slamming against the front of that wing and creating a lot of force. But hopefully this is streamlined, so most of the fluid actually goes over in a nice, smooth fashion, and we get hardly any drag associated with that, hardly any pressure drag. That's what the 0.02 is saying, okay? All right, and then 480 is my area. I'm gonna get a really large number. I got 2,211, okay? 0.6, so I'll call it 2,212 pounds of drag that way. Hey, I was talking some, and I probably should go through and check that really quickly. I lost confirmation. So 0.02, coefficient of drag, 230.4 dynamic pressure, 480 area. Yep. So a lot of drag on that, But hey, a lot of times there's probably the power worked out to get that plane moving. Okay, what's the lift going to be like? Okay, well, we could go step by step, but reminder, this number is going to be the same. This number is going to be the same. And what about the CL number? Well, it's going to be 50 times that number. So hopefully we could just take that number and multiply it by 50, and we'll get our answer. Okay, and I'm getting a very large amount. So 55 times this would be 10,000. I'm getting 100,000. 110,592 pound force of lift. And then we could start doing the calculation, say, given the size of our fuselage, the number of people we're carrying, et cetera, is this actually going to meet the need? Do we have enough area? Do we have the right drag and lift to make this all work out? Okay, that does it for topic 6. One last topic for test 3. All right, so last topic of the semester. Section 8.5 is pipe flow problems, and the book does a great job of having problems that really represent what's out there in real life. You're going to look at that at first and say, oh my gosh, how can I do this? Some of you maybe, but with a little bit of practice, you can do it. And of course, that's where you want to get. You've undergone some training to learn to do something complicated, and you want to be able to do something complicated so that makes you a professional. So when you look at the problems in this section right here, take a deep breath, break it down, and you're going to be successful if you do so. So for starters, you're going to see this equation referred to, and I'd like you to take a second just to write that equation down. I know my writing's a little bit small, so it may be hard to see, but the subscripts here are 2, and the subscripts here are 1. So I'll give you a second to write it down, and I'll describe what this equation is saying. All right. So this is essentially the extended Bernoulli equation with a couple modifications. Pressure energy, V squared over 2G, dynamic pressure or kinetic energy, and elevation energy, all expressed in feet, okay? Or there's some other ways of doing it. And we would use this equation in a situation where we had some flow, and we wanted to start here, and we wanted to come out here at 20 PSI, and we needed to say size pipe or do something like that. We would do this. Okay, this is very much like the Bernoulli equation. Energy at the end is equal to the energy at the beginning, but it could be less at the end than the beginning if there are losses. And of course, in reality, there's going to be losses. So the one thing that's the one thing that's particularly new in this equation, this is not that new. This is our specific fluid-specific weight, which is the same as rho g. We had that earlier in the semester. Okay, but this alpha here, what's that all about? Okay, well, quick reminder, the Bernoulli equation assumed that we were moving from point 1 to point 2 in streamlines. It assumes there was no viscosity. And if there's no viscosity, if we took a look inside a pipe, the profile would be uniform. Okay, well, in reality, the profile is not. There is a range of velocities from fastest in the middle to 0 at the edge there. So this V squared over 2G, it turns out, isn't an accurate representation of fluid kinetic energy in the case where there is viscosity. So there's some interesting work where an adjustment factor is incorporated. Fortunately for the pipe flow problems we're doing, like air and water, the viscosity is low, and so we end up getting turbulent flow. And if you remember, the turbulent flow profile is 0 at the edges of the pipe, practically uniform in the middle, with a quick rise to that uniform velocity profile. So there's turbulent. So turbulent is the velocity profile, is it more similar to laminar or is it more similar to inviscid? Well, for purposes of this calculation, it's more similar to inviscid. So we're going to use alpha equal to 1 for all our calculations. So please, when you see this step in the book, don't stress about it. They're going to stick with alpha equals 1 almost always, and we're going to stick with alpha equal to 1 always. So what we're going to do, though, is perhaps think about it just a little bit differently. Similarly, we're not going to worry about the alphas. And so our governing equation is essentially going to be equation 5.84. So last lecture, we took a look at chapter 5, and we wrote what's called the extended Bernoulli equation. And that's an equation you should already have down. Here's the difference. Well, first of all, here's the equation. Energy at the end, P2, V2 squared over 2G, Z2, is equal to energy at the beginning minus any losses plus any energy added by shafts, so H sub S. There's also equation 5.82, which is in terms of P over rho. The difference between the problems in chapter 5 and the problems in chapter 8 that we're finishing off in is now you know just about everything how to work these things out. So instead of this loss being given to you as a number, you're supposed to look at a piping diagram and think about how you can work that out. So that could be good enough. I could pause right now. I think it'd be really beneficial to look at an example similar to what you'll see on the homework and what you'll see on test 3. Let me get that up there and we'll get going. Okay, similar example to what you're going to see for homework in the book. It is an example from the book. I really encourage you to go through and do any example that's assigned on homework that gives you some guidance as you go through. Well, let's describe what's going on. Let's say we got a piping system and we're going to try to, water's going to come up here like this. It's going to make a turn and go horizontally. And we want the piping system to come out at 224 GPM and at 20 PSI. So let's say we already sized our pipe. We're going with 3-inch inner diameter pipe. Get that up there. Okay. We've got a pump here, all right? And so maybe we can pick out this pump to ensure that we have the required pressure at the outlet. And what pressure do we need actually at P1 at this outlet here to do it? Okay, well, the first step maybe would be to, let's see how it turns out if we ignore losses, is we just say, look, maybe we can approach this just using the Bernoulli equation. What kind of pressure do we need at 1? So I would encourage you to write the Bernoulli equation and see if you can crank through it and get what pressure is at 1. I'll once again be giving you a step at a time. See how P1 works out. Okay, well, there's the Bernoulli equation if we ignore losses. If we say, shoot, you know, this thing's going to go around this elbow, it's probably going to be fine. It's not going to lose us much pressure. It's going to go out this globe valve. That globe valve probably is not going to lose that much pressure. Maybe that pipe's pretty smooth, so it's probably all good. So that's going to work out pretty well. What are we trying to solve for here? We're trying to solve for the pressure P1. Okay, what pressure is required there? Let's just think about this, the dynamic pressure terms. Okay, well, if this were a constant inner diameter pipe, it would be a constant speed because the speed of a fluid is the volumetric flow rate over the cross-sectional area, so that'll be constant. Yeah, and just in general, what we're trying to do is get rid of any terms that we can. So we're going to get rid of those terms. Okay, what about Z1 and Z2? That's height, or that's elevation. Well, we can set the elevation anywhere to be 0 anywhere we want. And I think the smart thing to do would be to set the elevation right here at this first point, and then ignoring my drawing's not very good, but ignoring saying, look, an elbow is going to be small compared to 20 feet of pipe. Basically, we're going to say that Z2 is equal to 20. Hey, well, let's simplify that equation, maybe solving it first and see how it turns out. Okay, so I'm not as algebra oriented as the book. They do a ton of algebra, but here this is not bad. Z1 is 0, Z2 we're going to fill in later on is 20. I just went ahead and did the algebra, okay? And if I think about simplifying it, it's saying that P1 has to be bigger than P2 by this quantity right here. We've got to have enough pressure so that we get up there and have that 20 PSI. We're going to lose pressure as we go up. Okay, let's just go ahead and crank through the numbers and see what kind of pressure that turns out. Is that going to be like 21 PSI, 22 PSI? Let's check that out. Okay, so I did it the way we did it earlier in the semester where I got my density and I have my gravity. Of course, you can use gamma because gamma is in that chart. And if you're more comfortable with that, absolutely fine. So I cranked through my numbers and it's looking like, whoa, we're going to need the world's biggest pump here because we've got to get 20 PSI plus this number here. But hopefully you remember that that turns out to be pound per foot squared. And if I'm going to have to do pounds per inches squared, I'm going to have to divide it by 144. So that's going to be a lot more reasonable number. Divided by 144, and that's about 8.7. So I'm getting that we need 28 0.7 psi at the pump outlet. And that's a useful number that we could use actually to go further along in designing this system. It'll be interesting. You might get some situations where you're working with an engineer that's a little bit sloppy and they're saying, hey, I'm going to do it this way. The losses are going to be minimal. We're probably fine, but let's check it out. So I'm going to erase this and get you a little bit of more information up on the board, and we're going to take a look at how we'll incorporate the losses into our calculation. All right, so when we ignore the losses, we got 28.7 psi required here, pump outlet. We're going to include losses, and that obviously would be pipe losses. Let's say that our relative roughness is 0.006. We'll use that now. Okay, well, there's our basic extended Bernoulli equation. This is conservation of mechanical energy. The mechanical energy our fluid has at the end is equal to the mechanical energy it has at the beginning, minus any frictional losses, plus any work done by shafts. All right, so first thing to do is we would love to see if you can get rid of some terms. So I'll let you think about that for just a second, and I'm going to zero out some terms to make this a less daunting equation. Okay, so hopefully you did that. If this is a constant diameter 3-inch pipe, then the speed's going to be the same all the way along. And so these speed terms don't really end up changing, okay? We decided that we're going to make Z1 equal to 0, so that's still 0. Going from here to here, there's no pumps or fans or anything like that that does work. We defined our 1 at the outlet of the pump, so we don't need to worry about the pump. But there are going to be losses. Z1 we decided was 0, so that's it. So we actually already did this problem except for the losses. So now this just becomes a process in working out the losses, and let's think about how we do that. Okay, so pipe, you saw that on test 2. The head loss in a pipe is going to be the friction factor, L over D, V squared over 2G. So we know we can get going on that. What about the 90 elbow? Okay, well, that is that K value times V squared over 2G, where K is the loss coefficient. Okay, and what about the globe? Same thing, KL, where the KL is for the globe. So one thing that you'll notice when you do these pipe problems is that there's always a V squared over 2G term, or if you do it in terms of PSI, there's going to be that 1/2 rho V squared term. So let's go ahead and calculate V squared over 2G and see how it turns out. See if you can get all the way through that yourself. That would be good practice. Okay, so we like to be able to go back and forth between GPM and cubic feet per second. Remember that 1 cubic foot is 7.48 gallons. So that works out to be our flow turns out to be 0.5 cubic feet per second. And our area is pi times diameter squared over 4. And I got 10.2 feet per second. So hey, maybe this pipe is just a little bit small. That water's going on 10 feet in 1 second. But we'll go with it. And then V squared over 2G is 1.616 feet of head, where that is essentially equivalent to PSI in some sense. All right, we got that number here. Let's just go ahead and see if we can work these out really quickly. I'll give you some details. Okay, so starting with the pipe. So there's our expression for the pipe, and obviously we need to get the friction factor. I went through a Reynolds number calculation and I got 210,000. Wow, that's huge, very turbulent. But once again, water is low viscosity, and this water is really moving in a relatively small pipe. So I wish I had time to check this. I know a couple of you said, hey, it stresses you out a little bit. I hope you saw that on the test, the friction factor was really easy. In this case, I quickly got 0.032. Let's go with it. So let's go ahead and work out what the loss is for that pipe. And how much pipe do we have? 20 feet here, 30 feet there. We have a total of 50 feet of pipe. All right, in this case, the pipe is not insignificant. At least that's what I'm getting, and that's in part because the flow is so turbulent. So F 0.032, L over D, 50 feet of pipe, diameter of 0.25 feet, and V squared over 2G is 1.61. Let's go with 10.34 feet. And now let's move on to the elbow and to the globe valve. Okay, so doing the globe valves, we need to get the loss coefficient. And in this case, those come from table 8.2. For the threaded 90, we get a loss coefficient of 1.5. And a globe valve, we get a loss of 10. and that may seem pretty high, but they have a nice diagram of a globe valve, and you show like, wow, as that water goes through this globe valve, there's going to be a lot of rubbing, there's going to be a lot of friction. Well, just if you think a little bit algebraically, okay, both these have a v squared over 2g, and then they have their KLs. We could just work that all at once, where we could combine these two KLs into 11.5 and multiply it by v squared over 2g. So I'll just do that quickly on my calculator and see how that works out. So I got a 1.616 for v squared over 2g times 11.5. And I've got an 18.58 feet. Okay, I'm sorry, my writing was a little bit out there. So let's think about where we're going. We've got piping loss of 10.34 feet and fitting loss of 18.58 feet, and we can add those together to get our total loss. Okay, and I got 28.9. I'm just going to go with that. Our total loss is 28.9. Okay, where is that in this whole equation that we have up here? That's that term right there, 28.9. Okay, we're almost there. Let's finish it off. Okay, so taking a look at the algebra first, we're trying to solve for P1, and that's one way of looking at it, what I have on the right side here. And it actually hopefully makes some sense if we think about it. How much pressure do we need at 1? Well, we need a pressure so that we have enough pressure at 2, and then we need some additional pressure to overcome the elevation, which was 20 feet, and we need some additional pressure to overcome the losses. Looking at the numbers, well, this is 20 and this is 28.9. Those are both in feet, so we can add those. And so we get our pressure at 1 is going to have to be the pressure we want at 2 plus 48.9 times rho g. That, sorry about that, you guys, or P2 plus 48.9 times rho g. That turns to be out over 3,000, but that is pound per foot squared. So if we make it into pounds per inches squared, that turns out to be about 21.2. So 21.2 here plus 20, we need 41.2 psi. Okay, and comparing to what the answer that we got, if we said, hey, the losses are no big deal, 28.7, that is a significant amount of pressure. And so we would definitely want to keep track of the losses if we work that out. Okay, hey, that is the last example of the semester. I have a little bit of work to add to homework number 10. I'll be working on that tomorrow. Make sure that you've gotten through this lecture and the previous lecture with the examples, and do as much as you can on homework number 9. You'll get an email from me soon. Keep practicing. We'll be in touch.